So this is a short video about absolute values and other inequalities. I'm assuming here that you know what absolute values are and are fairly familiar with working with them. If not, please see the lecture notes for review. Most of the lecture notes is almost certainly very familiar from just doing absolute value calculations, but there are a few facts that may not be as familiar if you haven't done analysis before. And the first of them is called the triangle inequality. So it's this one here, with the triangle next to it. It says for all real numbers x and y, the absolute value of x minus y is less than the absolute value of x plus the absolute value of y. Okay. So if you haven't seen that before, I suggest taking a look at the lecture notes. There's an immediate consequence of the triangle inequality, which I think gets taught a little bit less, but is almost as useful in this type of class, and I usually hear it called the reverse triangle inequality, although it's just a triangle inequality rearranged. So here it is, for all pairs x and y, the absolute value of x minus y is bigger than the absolute value of x minus the absolute value of y. So it looks very, very similar to the triangle inequality, except that here I have a lower bound on x minus y instead of an upper bound. So how do you do that? Well, you just apply the triangle inequality to a sort of cleverly chosen pair. In particular, I'm going to apply it to x minus 0. So what do I get? I get x minus 0 absolute value is less than x minus y absolute value plus y minus 0. Okay, so I'm using the triangle inequality, except I'm sort of adding in this fake 0 over here. If I rearrange that, what do I get? Well, I put this x minus y by itself, move this y over here, and I find that x minus y absolute value is bigger than the absolute value of x minus absolute value of y. So very short proof, but worth remembering because it's very useful in a wide variety of situations. One thing that I suggest is trying exercise 1.6.5 in the textbook, in the lecture notes for practice or for review. There are a few other useful inequalities that we're going to be using in this course, although not really immediately, and so I'm going to review them sort of at the same time. The first of these is called the Bernoulli inequality, and it says the following: for every integer n, and for all real x bigger than or equal to minus 1, 1 plus x to the n is bigger than 1 plus n times x. So this is sort of a linearization inequality, right? It takes this function, which is a high degree polynomial, and replaces it with sort of a nearby linear function. When is this actually a good idea? Well, it's only going to give you a reasonably tight inequality. That is, those two sides are only going to be close to each other if x is quite small, and really if x is small compared to 1 over n. You can still use it in other situations, and sometimes it is still useful. If you don't need a very close bound, that's sort of the place where it's going to be the most helpful. Another inequality which you may have seen before is called the Cauchy-Schwarz inequality, and that says for all sequences a1 through an and sequences b1 through bn of real numbers, the sum of ai bi quantity squared is less than the sum of ai squareds, you can put in braces here, times the sum of the bi squareds, whole thing square root. When's that one good? Well, the two sides are equal if and only if the two sequences are in fact in the same direction. That is, ai is equal to some constant c times bi, and the inequality is going to be good if this equality here is sort of close to true. So if you think of a1, with the list a1 through an as a vector, and b1 through bn as another vector, Cauchy-Schwarz is going to be good if they're pointing in more or less the same direction, and if they're pointing in very different directions, it's not going to be so good. All right, I'm not going to prove the Cauchy-Schwarz inequality here. Probably many of you have seen the proof, and if not, it's sort of a little bit long for a detour, but I'll give a proof of the Bernoulli inequality because it's a nice application of the principle of induction. So how are we going to prove Bernoulli's inequality? So just to sort of as a recap, it's saying that 1 plus x to the n is bigger than 1 plus nx. We're going to prove it by induction on n. For n equals 0 or 1, it's sort of obvious, right? When n is equal to 0, this is 1, and this is 1 as well. When n is equal to 1, it's also obvious, 1 plus x to the 1, so this is 1 plus x, and 1 plus n times x, so 1 plus 1 times x. These two sides are exactly the same again. For n equals 0 or 1, then, it's clear. So that's going to be the base case. And now we're going to prove the induction case, but it's going to look a little funny. We're going to skip 2 instead of skipping 1, which is why we did 2 base cases at the beginning. So let's assume that Bernoulli's inequality is true for n and true for n plus 2. And we're just going to do the obvious algebra. 1 plus x to the n plus 2 is equal to 1 plus x to the n times 1 plus x squared. We're going to use the base case to expand the first term, and the second term we can just do. It's 1 plus x squared is 1 plus 2x plus x squared. And the next bits, I'm just doing a bunch of algebra, so I'm not going to comment on it too much. But what do I get after a bunch of algebra? I get the thing that I'm interested in, 1 plus n plus 2x. So that's the thing that shows up in Bernoulli's inequality. And then I get this extra term. And I just got to check that that term itself is positive. So n is obviously positive, x squared is obviously positive. And then I have this 2 plus x. Well, that's going to be positive as well, because x itself is bigger than or equal to minus 1. And so at the end of the day, I get exactly what I want, which is that this whole term is bigger than 1 plus n plus 2 times x. Why do we bother with any of this sort of stuff? Well, the point of doing the Bernoulli inequality is the following. When the absolute value of x is very small, this is almost an equality. But as you can sort of see, the calculations are much, much easier. It's much easier to deal with a linear equation than it is to deal with this sort of crazy high degree polynomial. So that's what I'm doing with all of this. And as soon as we start talking about sequences and limits, we're going to be using this fairly frequently. Thanks.